Okay, so these are just a few more practice problems for inclines, and I'm going to go ahead and get our incline drawn here. Remember that the right angle always goes opposite of our hypotenuse. Okay, we never make a right angle with our gravity vector. Okay, the right angle always needs to go opposite of that gravitational vector. Okay, right angle always goes opposite. And what would I label this side as right here? Normal force. And the bottom would be the parallel force because it runs parallel to our surface. Okay, we can also draw the normal force above the incline just to give ourselves a little bit more of a view. You don't necessarily have to do that, especially in this case. We're missing one other force here. Friction, okay, because our overall goal is to find the coefficient of friction, which means there's got to be a frictional force. So what direction does the frictional force go here? With the incline or against the incline? Against the incline. Okay, so it needs to go up. Okay, so first and foremost, let's go ahead and, where does our 25-degree angle go in our gravity triangle? Here, here, or here? Right there, okay? So this is 25 degrees. So first thing that we do is we need to solve for the components of that gravitational triangle. So we need to solve for F sub n and F parallel. Okay, what do we know about the force due to gravity? How do we find that force due to gravity? M times 9.8. Okay, and our mass, they told us, was 11 kilograms. Okay, which means our force due to gravity is 107.8 newtons. So that right there is our hypotenuse of that gravitational triangle, 107.8 newtons. Okay, that's going to be our hypotenuse. So to solve for our normal force, we're going to take hypotenuse, 107.8, times sine or cosine. We're going to use cosine because it's adjacent to that 25-degree angle. Make sure that your calculator is in degrees, not radians. Okay, do we agree with that value, 97.7? Okay. And solve for force parallel, we take our hypotenuse times sine or cosine? Times sine. Okay. So now that we've got both of these components here, we can start looking at our overall goal. And our overall goal is to find the coefficient of friction. So if we're looking at this frictional force and the coefficient of friction, are we going to be using the vertical forces or the horizontal forces? Horizontal. And how many horizontal forces do we have here? We have two horizontal forces. First of which is force parallel. Second of which is the frictional force. Okay? Even though it's not drawn from the center, we could draw it up here if we want to. Force parallel. If that makes you feel better to have everything coming out of the center, that's fine. But we still have two horizontal forces. The parallel force is the gravitational force that's pulling it down the incline. Frictional force is opposing that. Okay? So let's go ahead and set up our net force equation in the x direction. Which of those two forces is heading in the positive direction or pulling the object in the positive direction? The parallel force or the frictional force? Parallel, right? Because we tilt our axes when we work on an incline. So we're going to take our parallel force minus our frictional force. Now, what's this little nugget right here tell us? Constant velocity. That our net force is 0, or acceleration is 0. Okay? So this means 0 is equal to force parallel, which we found to be 45.6, minus, what can we substitute in for the frictional force? What's our equation to solve for the frictional force? Mu times the normal force. Good. So we can substitute this in for our frictional force. Mu times the normal force. What do we know that the normal force is equal to? Yeah, 97.7. Oops. And this little Greek letter here is our mu, or our coefficient of friction that we are solving for. Okay, so we can add that whole term to the other side if we want and get 97.7 times mu equals 45.6. All I did was add this whole term to the other side. And then to solve for mu, I divide by 97.7. Does this coefficient of friction fall within our general range? Yeah, typically what do we want our coefficient of friction to be between? 0 and 1. We typically want that coefficient of friction to be between 0 and 1. Sometimes it'll hedge over 1 a little bit, but for the most part it stays between 0 and 1. Do we have any other forces acting here? No. Okay, because it says it's frictionless. And first and foremost, what does this 450 newtons tell us? It tells us it weighs that, which means that's equal to F sub g. Okay, you do not take that value times 9.8. Do not take that value times 9.8. Okay, that's equal to F sub g. They did that work for you. Okay, they did it for you. So the way that you can tell, if you can't tell just by contextual clues in the problem, you have to look at the units. Okay, the units of a force is always newtons. The units of mass is always what? Kilograms. So mass times 9.8 would give you a force of gravity. kilograms times acceleration gives you the force due to gravity. When it's in newtons, we do not take it times 9.8. Understood? Okay. If we want to find the mass from 450, how would we do that? We would divide by 9.8. And we're going to have to do that here in a little bit, but we'll just go from here for right now. All right? So let's start by finding the components of our gravitational triangle. Okay, the normal force, we're going to take 450, which is our hypotenuse, times cosine of 30 degrees. And for our parallel force, we're going to take 450 times sine of 30 degrees. Okay, that's the first thing that we do before we start looking at anything else, is find those components. Okay. Our overall goal from the problem says, how long will it take the object, starting from rest, to get to the bottom of the incline? What variable overall is our goal to be solving for here? Yeah, we're trying to solve for time, okay, which means we're going to have to use our kinematics equations. But what variable must we have before that to use our kinematics equations? Acceleration. Good. We have to find acceleration. And are we looking for acceleration in the vertical or the horizontal direction? The horizontal direction. Okay, so let's go ahead and set up our net force equation in the horizontal direction. How many horizontal forces do we have? We have one, right? And that one horizontal force is parallel, F parallel. Okay, we don't have anything that's opposing that force, so we're not subtracting out anything. Okay, we know the parallel force is equal to 225, and we're solving for A, so we need to take it times its mass. Okay, so are we taking it times 450? No. Okay, so we need to find its mass based on that force due to gravity. So since we know F sub g is equal to 450, we're going to take mass times 9.8 equals 450, and we're going to divide that by 9.8. Okay, we get 45.92 kilograms, which I'm going to substitute in here for mass. Okay, to solve for A, which am I going to divide by 225 or am I going to divide by 45.92? Divide by 45.92. Okay. And that gives me an acceleration equal to 4.9 meters per second squared. Good. Okay, our overall goal we know is to solve for time. So let's think about what kinematics equation or kinematics variables we have. We have acceleration. What else do we have? Distance final, which is equal to 9 meters, right? Because it tells us the incline is 9 meters long. We're assuming we start at the top of the incline, and we're going to travel all 9 of those meters. What else do we know? Yep. We know its initial distance is 0 because that's our origin. We know that v sub I is equal to 0 because it tells us it's starting from rest. Okay. So what kinematics equation can we use to solve for time? Yeah, the second one. Okay. I'm going to probably run out of some room here. But we're going to use the equation df equals d sub I plus vit plus 1/2 at squared. Okay, so 9 equals 0 plus 0 plus 1/2 4.9 t squared. Okay, so let's go ahead and try this one on your own. So we got a final velocity somewhere around 12.9, hopefully? Yeah? 12.7? Okay. That's just because I rounded my parallel to 13.